So the first thing that I definitely want to hit on is the shapes of the d orbitals. So I'm going to draw a Cartesian axis up in the upper left-hand corner of this page. And just like in physics class, we can label this axis in any way that we want. We're going to say the z-axis is pointing straight up and down. The y-axis is listed here, and then the x-axis is coming in and out of the page. So here's our Cartesian axis, and this is how we set things up. And we can then draw in the various d orbitals. There are 5 different d orbitals. The first is the dz squared. The dz squared has an orbital lobe right along the z-axis, and it looks just like a p orbital with a big donut in the middle of it. So this is what our dz squared orbital looks like. The x squared minus y squared orbital lies directly along the x and the y axis. So if we draw these out, and here's our x and our y axis, these orbital lobes are going to fall directly along the x and the y axis. So this is what our dx squared minus y squared orbital will look like. The dxy orbital is the exact same shape and the exact same size as the dx squared minus y squared, but the only difference is that rather than sitting right along the x and the y axis, its orbital lobes are going to point directly in between each of these axes. So this orbital is going to look something like this. And the key point here is that the orbital lobes point directly in between your Cartesian axis. It's easier to see sometimes when we draw the dyz orbital. And again, the dyz, the dxy, the dx squared minus y squared, and the dxz are exactly the same shape, and they're these 4-leaf clovers that point directly in between these axes. So the dyz is pointing straight up and down like this, and the dxy is kind of like this, and then the dyz would be like this. They're all rotated in space. The dxz is the toughest to draw with this coordination axis, and it's going to have a lobe here, 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 and here, and it's going to be kind of tilted at 90 degrees, and it's going to have the exact same shape as all these other orbitals. But the key thing is, how are these orbitals oriented in space? And typically, when we're analyzing these transition metal complexes and looking at their orbitals, we group these orbitals into 2 different sets. The first set is the dz squared and the x squared minus y squared. I'll call this set number 1. And set number 1 has orbital lobes that lie along the Cartesian axis. We then can group the xy, yz, and xz and call these set number 2. In set number 2, the orbital lobes lie in between the Cartesian axes. And this is going to play an extremely big role in how it's going to overlap with the various ligands that are approaching this transition metal center. So for set number 1, we're going to have a strong interaction, or we could say a strong overlap with ligands along the X, Y, Z axis. And likewise, we would have a weak interaction with ligands in between the axis. For set number 2, we're going to have a weak interaction with ligands along the X, Y, Z axis. And we're going to have a strong interaction with ligands in between the Cartesian axis. So when we develop our energy diagrams, we need to keep these interactions in the back of our mind. Likewise, we can draw the 4s orbital, which extends into space like a basketball, and the spatial extent, or how big this s orbital is much larger than the 3D orbitals. So the 4s orbital, since it's completely spherical, has a strong interaction in all geometries. And we can say this is highly symmetric or completely spherical.